Hey, PChemsters, this is Mrs. Vanderlein bringing you another blank wall. This is section 7.5, the quantum mechanics and the atom. So we're going to start off with the Schrödinger wave equation. So this is kind of a response to what do we do with other elements. If you go back a few sections, you'll notice that everything we've been talking about could only work with hydrogen. So the Bohr model only works well with hydrogen. So what are we going to do about the rest of the atoms and their electrons? Because obviously there's more to life than just hydrogen. So what Schrödinger did is that he came up with this wave equation, and what you see right there is the wave equation, and you probably go, what the heck is all this stuff? And I just want to kind of bring your attention to this symbol right here. I don't know about you, but it kind of looks to me like the Poseidon's trident. And I mention that because that is the Greek letter Psi, PSI. And what Schrödinger says that this is going to be the variable to solve for the probability of finding a certain electron. Okay, so he used the idea of Heisenberg's uncertainty principle, and he combined that, and he was a mathematician, really. He wasn't truly a well-known scientist. He was a true mathematician. And what this does is when you solve for this three-dimensional region, notice that we're talking about second derivatives here, this three-dimensional region, that is the probable location of finding the electrons. Now, it says that prove the quantized of electron energy is the base of quantum theory. This quantum theory describes mathematically, notice I said that, the wave properties of electrons and other very, very small particles. And what this does, it shows that we don't just move the electrons around in this planetary orbit like this circular path, if you will, all right? So instead of calling them orbits like Bohr did, all right, he's the one that came up with the solar system model. So what Schrödinger did is he revolutionized this, and he says we're going to call this orbitals, not orbits, orbitals. All right, so what is an orbital? It is a three-dimensional region. And so what happens is that the answer to this mathematical problem, all right, is this three-dimensional region around the nucleus that indicates the probable location. So in addition, it shows that energy must occur in integer multiples. So what I've done here is here are my SPD, and shortly I'll show you the F. And the sphere, these what I call the peanuts, these what I call daisies and a dumbbell, these are all answers to that equation above. So this perfect sphere is an answer to that equation above. These three peanuts are perfect representations of the equation above. And notice I had said earlier that this is a mathematical. Look at the mathematical, look at what I'm trying to think of, the relationships, think of the patterns, that's what I was trying to say, that has been established. So there's one sphere shape, there are three P shapes, there are 5 D shapes, okay? If I scroll down, guess how many Fs there are? There are 7 F shapes, okay? And let's keep looking at this. There's just one lobe. Here I have 2 lobes. Here, these 4 right here have 4 lobes, and this is my dumbbell shape. All right, let's look at the Fs here. Notice that there's 1, 2, 3, 4, 5, 6 of them that have 8 lobes, okay? And again, very, very mathematical, okay? So let me just kind of look at G. What about G? How many G orbitals do you think we have? We have 1s, 3p, 5d, 7f. How many G's do you think we have? Well, hopefully you said there are 9, all right? And what about their shapes? Well, I ran out of acronyms, maybe a geranium, I don't know. So I'm not going to come up with that. But again, how many lobes do you think, 8 of them are going to have? Well, if you said 16, then you are correct, okay? So look at the mathematical progression that Schrödinger did, and this kind of broke open a huge idea then with the idea of this atomic stuff here where the electrons are. And now we can look more at where are these electrons, because that's where all the bonding occurs. That's where pretty much all the chemistry occurs, is where the electrons are. If you want to talk about nuclear, we can talk about the nucleus, we can talk about the protons as well, and the neutrons. But for the majority of all chemistry, we want to know where the electrons are. And so Schrodinger broke this open and really gave us a better picture of what's going on, much more comprehensive than the Bohr model, the planetary model. So let's see what happens next. So not only are we talking about the electrons themselves, so let's talk about the energy of these electrons, okay? So now that we have, these are my principal energy shells, okay? Same idea what Bohr had, okay? And so if I have an electron at the ground state, that's where n equals 1, and it jumps up to n equals 3, it's going to absorb energy, okay? Well, how does that electron get back down, all right, to the lower energy? Is going to emit energy in the form of light, and for the majority. Now, we can also emit it in the form of UV or in the form of IR or gamma or whatever, okay? So it all depends on how much energy it has to absorb and how much energy is released as to what form of energy the photon is going to have, okay? So if it is off of the ground state, it's considered excited. It's gained energy. It's excited to gain energy. Let's put it that way. So now what can we do is that we can come up with some numerical values here. Okay. So delta E is E final minus E initial. Let me scroll down here. So again, I don't know if you really want to know where these numbers are coming from, this negative 2.18 times 10 to the negative 18th joules, but it's 1 over n squared, the final, like where, if it's going to absorb energy, it's going to jump up here where it ends up. So this would be your initial, that's your final, or if it's releasing energy, this is your initial and that's your final. So that's what these numbers are representing. Which energy shell is it starting from? That would be over here. Where does it end up is over here. So it all depends on, you got to watch really, really closely that if it's jumping up or jumping down, okay? So that's where you're going to put your NF and your NI, okay? And when we're all done, this is the equation that you're going to use, okay? And so I starred this. It's the one that we're going to use from here on out, okay? So what happens here, calculate the energy of an electron in a hydrogen atom to fall from the orbital where n equals 3 to the orbital where n equals 2, okay? So where is it starting from? Well, it looks like it's starting at 3, so it's my initial. That's my second number, isn't it? Where is it ending up? It ends up where n equals 2. That's where my final is. That's my first number. So I'm going to do this. Now, in math class, what should you do next? You should go ahead and, what is 1 over 2 squared? That's 1 over 4. Well, what's 1/4? That's 0.25. Minus, well, what's 1 over 3 squared? What's 1 over 9? That's 0.11111, right? So what's 0.25 minus 0.11111? And you're going to find it is equal to 0.139, okay? And then what? So just multiply these two numbers together and you get negative 3.03 times 10 to the negative 19 joules. So why is that important? It's a negative number. And why is being negative important? This is energy. So what does that mean if energy is negative? Is it endothermic or exothermic? Oh, it's exothermic, isn't it? Let's scroll back up again. So if I'm going let me go back here, from 3 to 2, I'm going down from 3 to 2. Energy is being released. How is it being released? In the form of a photon. The main idea is energy is being released. It must be negative. Okay, so that has to be consistent. So what now? Note the energy is negative because the atom releases energy to go back down to a lower state. Well, how much energy did that photon absorb? Notice it's going to be, if it's going to absorb, think that, I spelled absorb wrong. Here, let me fix that. Oops, sorry about that. There we go, that looks better. So anyway, if it absorbs energy, what does that mean? It's endothermic. If it's endothermic, what is the sign? Well, the sign is positive. All right, why? Because energy is absorbed, okay? All right, let's go on to the next page. Problem 12 says calculate the energy for the electron in a hydrogen atom to fall from the orbital where n equals 4. Your thing probably says 3. Let's make it 4 because we just did 3. All right. So why don't you go ahead and do this one totally on your own. So as always, pause this and figure out this energy. Okay. So when you're done, come back. All right. How'd you do? Well, I set this up. Notice that my final minus my initial. So I start at 4 and I fall to 3. So what kind of number do you think this is going to be? All right. I am going from a higher orbital to a lower orbital. Energy has to be released. So my value ought to be a -1. All right. So when I did the math here, yes, this is a 0.1875. Notice there's not really any sig figs involved here. And so when I multiply these two numbers together, I get -3.9 times 10 to the -19th. So I wrote, no, this is more energy released, right, from when n goes 4 to 2 than from n to 3 to 2. And does that make sense? Oops. Sorry about that. If I had n equals 4 up here, all right, wouldn't it take more energy released to go down to 2 than from 3 to 2? Yes, it does. Not a whole lot, but yeah, it does take some energy. Let's go continue on now. So remember, this energy is released in the form of a photon. So whatever energy is released, well, what's the energy of that photon? It's just the positive value of what you saw for earlier. Notice I don't have a delta E, I just have the energy, not the change in energy of the photon, just the energy of the photon, all right? And it's that positive value. And now we can find the wavelength. How are we going to do that? Well, didn't we just learn about the de Broglie wavelength? All right, what was that equation for the de Broglie wavelength? Well, let's find out. Do you remember this from, I don't know, what was it, 7.4? Well, hopefully you do. All right, it wasn't that long ago. So what I did is I rearranged the equation. So I just made wavelength, there's that lambda is equal to hc over E. And now I can plug in some numbers. There's my Planck's constant. There is the speed of light. And there is my energy. Look what I can do here. Whoops, sorry about that. Trying to get a pen going here. Here we go. So notice that the joules cancels out. Notice Joules. Oh, sorry. Notice that the seconds cancel out. So what unit is left? Oh, the meter is left, all right? So when I actually solve for that, I get 5.1 times 10 to the -7th meters, all right, which is 510 nanometers. Why would I do that? Because I want to know where it is. Hey, that's in the visible light, isn't it? Just kind of going on with this. It's in the visible light because visible light's from 400 nanometers to 700 nanometers. So, yep, this is indeed visible light, okay? So that wasn't too bad, was it? Let's see what the next problem is. I should probably throw this in. See, chemistry does make sense. Love it. All right, go on to the next problem now. All right, so you might see that we have some values here. So we have 434, 486, 656. So what do you notice, just real quick? Here's the visible light. So if I go from 5 down to 2, I should get a larger jump. But look at the wavelength. It's a shorter wavelength. Here I have a medium jump, 490 or 486, all right. And then here is 656, all right? So notice that the lower the jump, the longer the wavelength. What does that tell you about the relationship between energy and wavelength? Again, it's inversely proportional. We saw that in section 7.4. So notice that these are kind of like medium lengths. Notice these are really long lengths. So if it's really long lengths, so if energy is really high, what would wavelength be? Really, really, really low. Well, that's your UV, isn't it? So what if I have really short little stubby ones here? So what if energy is really low? Then wavelength is going to be really, really high, right? And so that would be your infrared wavelengths. And what I put down here is I go notice that energy and frequency are inversely proportional to wavelength. So to answer the next question here, all right, let's see here. Which results in the emitted light with the shortest wavelength? Well, what would that mean? The one with the what? Largest energy jump. Well, look at these pictures up here. All right. What would be my largest energy jump from 5 to 4? What else do I have? 4 to 3 or 3 to 2? Which is my largest jump? Well, hopefully you picked 3 to 2. Okay. All right, so let's go ahead and determine the wavelength of light emitted when an electron in a hydrogen atom makes a transition from n equals 6 to n equals 5. So why don't you pause this and do the problem. Notice like a two-stepper. You got to find the E of the light, find the E of the photon, then you can find the wavelength. Okay, go for it. All right, I didn't type this out, but hopefully you can still read my handwriting. So here's my work. Notice my final is 5, my initial is 6. So I am going from 6 down to 5. I'm releasing energy. So the energy is negative 2.66 times 10 to the negative 20th, I believe, joules. And then I use the E equals h nu. All right, and I reverse the E in the lambda. So I end up with 7.47 times 10 to the negative 6 meters, which is 7,470 times 10 to the negative ninth. Why would I go to the 10 to the negative ninth? Well, because I want to go to nanometers, and nanometers is 10 to the negative ninth is nanometers. And so it's 7,470 nanometers. All right, that's a huge wavelength. All right, much lower energy. How do I know that? Because this is to the negative 20th. Visible light will be 10 to the negative 19th. Okay, so I know it's lower energy than visible light. My wavelength is really high, much higher than red, which is 700 nanometers. I'm not even sure this would be in the infrared. This may be more of the radio waves or the microwaves, okay? So it's even less energy than just infrared, okay? So does that make sense? Well, let's scroll back up again. You're going from 6 to 5. That's going to be a smaller jump if this were in proportional than anything else. And this is in the infrared wave, so I'm not really sure what this is going to be. All right, it could be microwaves, could be radio waves. All right, let's go to the next problem. All right, so why don't you go ahead and do problem number 15 on your own. And remember, it's a two-parter, so go ahead and do that one. And when you're done, come back. All right, let's see how you did. All right, so notice that my initial is n equals 2 and my final is n equals 7. So I'm absorbing energy, aren't I? You need to absorb energy to go up. So let's see if my numbers kind of worked out that way. Well, when I did this, I got negative 0.2499989, all right. And then what? Well, what's a negative times a negative? It's a positive. Did you catch that? It's a positive. So that's the amount of energy absorbed to go from 2 up to 7, okay? Well, if I'm going to have that wavelength of the light absorbed, so once again, I'm going to use the same E equals h nu, or hc over lambda, sorry about that, and I plug in these values, and what do I get? Come on down. Oops, need to scroll down a little bit more. There we go. So notice what happens. I said I got 3.65 times 10 to the negative 7th, which is 635 nanometers. I said it may be visible light, but it's more likely to be UV light. So you're going to have a smaller wavelength, a larger energy, okay? And so that makes sense to me, okay? Let's see what the next one is. Okay, look at problem number 16. Look what's going on here, all right? You only know one level. It starts off at 6, and it's going to emit a light, a photon of 993.8 nanometers. And this is maybe a little more realistic because we can see these lights, all right? We can see those lines. So we can measure those nanometers. And so now they said, well, if it starts off at 6, where does it end up? All right, so what we need to do here is find the energy of this, and I'll use that same equation again. And then what we have 0.938 times 10 to the negative 7th meters, because notice it's 93.8 nanometers, not like 193 or something. So watch how you move your decimal point. And so when I calculated it, I got 212 or 2.12 times 10 to the negative 8th. And that's equal to negative 2.18 times 10 to the negative 18th joules. And notice my row, I goofed, didn't I? Hang on, let me fix that. Whew, I'm glad I caught that, all right? So it's final minus initial, isn't it? So my initials in the sixth thing, we're trying to find out what this is. Now, why did I make this a negative? Great question. Because remember, the energy released equals the energy absorbed. So this positive 2.12 times 10 to the negative 18th is the energy absorbed by the photon, all right? So now the energy that was released is 2.12 times 10 to the negative 18th, all right? So then when I scroll down a little bit more, look what I'm doing here, all right? And so what I do, I divided each side by negative 2.18 times 10 to the negative 18th. So negative 2.02 times 10 to the negative 18th divided by that is 0.972 equals 1 over n squared minus 1 over 36. Well, 1 over 36 is 0.0278. Add that to both sides. 1 over n squared equals 0.9997. So for all purposes, n equals 1. All right, it can't be n equals 2 because we know that 1 over 2 squared is 1/4, or just 0.25. So obviously, that's a reasonable number. Okay, so once you problem 17 on your own, we're done. Come back. All right, so here's the equation. Now I paused here for a second because you're going to actually remove the entire hydrogen atom. So we had to understand what NF and what Ni is. So if it's from its ground state, Ni, that should be an easy peasy one, N equals 1. But what's NF? You're totally removing it. So let me scroll back over here again. N equals affinity. So what does that mean? You totally ripped it out of its shell. Okay, you've totally taken it away. So that's what infinity is right here, is when you totally removed it. So I have 1 over, it should be infinity squared. Sorry, I didn't put the square in, but you know what? What's infinity and infinity squared? That's really the same number, isn't it? And so what is 1 over infinity? What's 1 over a huge, 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 huge number? Isn't it 0? All right, think about that. And then what's 1 over infinity squared? It must really be 0 then, okay? So this number cancels out, and 1 over 1 squared is, well, 1. So what is negative 2.18 times 10 to the 18th times negative 1 is positive. All right, so it's the energy required. All right, so that's how much energy is needed, is absorbed, if you will, to remove the electron from the hydrogen atom from its ground state. So that's why it's a positive number. All right, so I'm done with 7.5. It went 23 minutes about. So hopefully that will help you. Hopefully it's somewhat review from what you learned in honors chemistry. And we'll see you next time. As always, don't wait to be great. Bye.